The following program is brought to you by Element 14, the electronics community where you can connect and collaborate with top engineers from around the world. Join now at element14.com/presents.
Hello and welcome back to Element 14 Presents. I'm Andy West, and in today's episode we'll be building our very own synthesizer. The word synthesizer covers a wide variety of electronic instruments, both large and small, analog and digital, and hardware and software based. But today we're going to make something that's actually more of a sound module. I'll explain. This is my new keyboard. You notice that when I press the keys there's no sound. It's not broken. The reason we're not hearing anything is because this is a MIDI controller keyboard. When you press the keys or move the controller wheels, the keyboard generates MIDI messages. Those messages are then sent via cable to another device that produces the sound. And that other device is what today's build is all about. Alright, it's time to bring out my trusty old FPGA board and my questionable keyboard playing skills, and we'll try to make some music.
Let's get started.
Amazing hacks. Inspired designs. Each week, Element 14 Presents brings you innovative projects using electronics, engineering, and more.
Let's go over to the virtual whiteboard and work out the design of our sound module. Here you can see we've got our MIDI keyboard, FPGA, and either amplified headphones or speakers. Now you might think that we could just split the wires in a MIDI cable and wire them directly to the GPIO pins on the FPGA board, but that's not the case. We need a MIDI breakout board built to the right specifications, and then on the other side we'll need something called an I2S decoder. This will take a bit stream from the FPGA and convert it to line-level stereo output. Once these breakout boards are in place, we can connect our components with the appropriate cables. We'll also need a breadboard, power supply, and level shifter to protect the FPGA's inputs. And I'll get into those in more detail as we start to build our project. I figure we'll start with some soldering. The MIDI board I chose comes as a kit that needs to be assembled. Now there are actually two different kinds of MIDI connectors that are common. One is USB and the other is 5-pin DIN. This board has DIN connectors, so if your keyboard is USB only, then you'll have to get an adapter. Following the online instructions, we carefully solder each component, being mindful of components that have to be installed in a specific direction, like this IC and this diode. Next we've got our I2S DAC, so we'll go ahead and solder on the pin headers. And then we've got a 4-bit bidirectional level shifter. We're only going to use 2 bits here, but that's not a problem. We'll solder the pin headers on here as well. Finally, we've got this breadboard power supply. I find these super handy and they can be powered off USB or a wall adapter using this barrel type connector. Each power rail can be configured with either 5 or 3.3 volts, and it's even got its own power switch. Now we'll round up the rest of our parts and wire everything up. We'll start by taking our DA converter, or DAC, whichever you prefer, our level shifter, and our power supply, and arrange them all nicely on our board. Then with a few jumper wires we'll connect our power and ground. Next we'll bring in the MIDI board. The positive and negative pins go to power and ground, of course, and receive and transmit go to bits 1 and 2 of the level shifter respectively. This is on the higher voltage side. Now it's time for the FPGA, which is the brains of our system. And if you've seen my previous videos, then you know that my go-to FPGA board is the DE0 Nano. This device is highly versatile and reasonably priced, and I can tell you that it's great for beginners because it's the first FPGA that I ever used. We'll connect everything to GPIO header 1 for convenient placement. There are lots of pins on the soundboard, but we're only interested in 3: word select, also known as left-right channel select, data in, and bit clock, and those are wired to the last 3 GPIO pins. You remember that our MIDI board is using bits 1 and 2 of the level shifter on the 5-volt side, so now we'll run 2 jumper wires from the other end of this pin header to bits 1 and 2 on the 3.3-volt side. And again, the purpose of this is to shift voltage down and prevent damage to the FPGA. We'll take a single jumper wire and connect a ground pin on the FPGA to ground on our breadboard. And there you have it. We're ready for our keyboard and speakers. There's a whole wide range of prices and features when it comes to MIDI keyboards. If you're on a budget, you can find decent ones for about the same price as a Raspberry Pi 3B+. I chose this one partly because it has the 5-pin DIN-style MIDI ports that I mentioned earlier. We'll plug one end of a MIDI cable into the out port of the keyboard and the other end into the in port of the MIDI breakout board. When it comes to speakers, you've got tons of options. Really anything with line level input should work, but I don't recommend headphones unless they're powered or you have a separate headphone amp. I went for this Bluetooth speaker with an auxiliary jack, and we'll plug it into the DAC using a 3.5mm stereo audio cable. Last but not least, we need to power our board. I'm using a common micro USB charging cable, but you can use whatever's most convenient for your situation. This is a straightforward circuit to assemble, but now we're getting into the tricky part where we code our synthesizer in Verilog. As I always say, the best way to tackle a big task is to break it down into smaller parts, and the first part to programming our synth is setting up a project in Quartus 2. I've used the system builder to create the new project and I named it Sound Module. At the start of the top level module we have our ports, which match up to the physical wires we connected previously. In addition, we've got this 8-bit register called LED. There are 8 LEDs on the Nano, which are useful for debugging and other purposes. In the pin planner, we configure the corresponding pins, and I like to use this online reference as a guide, since it's easier to read than the official manual. Our sound module has 2 main parts, the input, which takes in a MIDI signal and processes it, and the output, which generates sound. So for that we've got 2 additional Verilog modules, one called MIDI processor, and one called Synthesizer, and we instantiate them here in our top level module. These modules need to be connected, and we do that with wires. For example, the is-no-on wire connects an output register in the MIDI module to an input in the synthesizer. Next comes the always block. The code in this block executes based on changes to values in the sensitivity list. In this case, it just contains the positive or rising edge of our 50 MHz clock. A clock is basically a square wave with rising and falling edges. Within the block, we connect the synthesizer output registers to the corresponding I2S output ports. We also light up the LEDs when a node is on. Now it's time to process the MIDI signals coming from the keyboard. MIDI defines a communications protocol as part of its standard. A byte can be either a status byte or a data byte, which is determined by the most significant bit, 1 for status bytes and 0 for data bytes. A MIDI message is composed of 1 status byte followed by some number of data bytes. This is one of the most common and most important MIDI messages, note on. The status byte consists of 2 parts, the message type and the MIDI channel. 9 is the note on message, or 1001 in binary. Up to 16 individual channels are possible, but since we're making a monophonic synthesizer, the channel information can be ignored. The first data byte determines the pitch, or frequency, of the note. The second data byte represents the velocity, or force, with which the note is played. To keep things simple, we'll also ignore the velocity value. In our MIDI processor module, we've got quite a bit of state to maintain. For example, we've got the current status, or message byte, and the channel. We've got the data bytes for the current message, and we also track how many data bytes have been received so far. Here we're instantiating even more modules to help us process the MIDI signal on a low level. But before we get into those, let's look at our always block. There are several dozen lines of code here, and it's all wrapped in an if-else-if conditional. The top part executes if a byte is available to process. If it's a data byte, then the most significant bit is 0, which means the value is less than hexadecimal 80. We can store up to 3 data bytes, and in each case we're incrementing the received count and setting the data byte available flag. If the byte is a status byte, we split it into status and channel values and reset the count of data bytes. This else-if section only runs if a data byte specifically is available, and here's where things get interesting. This case statement looks at the message type. Node on and node off occur when we press and release the keyboard keys, and controller change fires when we move the modulation wheel up and down, for example. We'll use this modulation value later for some cool effects. Let's hop over to the MIDI byte reader module and see how to handle the MIDI signal at the bit level. The first thing we do is declare a couple of parameters related to timing. Standard baud rate for MIDI is 31,250 bits per second, which is convenient because it divides evenly into the DE0 Nano's 50 MHz clock. Debounce ticks is the number of clock cycles that we count down to ensure a stable value. This is necessary because a physical switch doesn't provide a perfectly clean signal when you press it. The value sort of bounces up and down extremely fast and looks like multiple switch presses. So debouncing allows us to filter out that noise. The rest of our parameters and registers are used in the always block as part of a state machine. And this is very timing sensitive. We watch for a signal, then capture all the bits for a complete byte, and finally make that byte available to the MIDI processor module. And we just cycle through those 3 states over and over. The last MIDI-related module is MIDI note number to sample ticks. The MIDI note number is a number from 0 to 127 that indicates what key has been pressed. Now, most keyboards don't have 128 keys, so to deal with this, you can move up and down the octaves, usually by pressing a button. Each note number corresponds to a frequency, which you can see in this chart. We could use a formula to calculate the frequency on the fly, but that would be inefficient. We'll pre-calculate a table with the number of clock ticks to count between each sound sample. The formula is clock frequency divided by note frequency divided by samples per cycle. Clock frequency is again 50 MHz, divided by the note frequency from the chart, divided by samples per cycle, which is 256. I'll explain this more when we talk about synthesis. I wrote a simple tool to generate these values and save a whole lot of typing, as well as prevent errors. We're now able to process MIDI signals, detect key presses, and get the number of sample ticks for the note we want to play. And we can display the last 8 bits of that number on the Nano's LEDs. Let's try it. These varying bit patterns are a good sign. They tell us that our code is working. Sweet! It's time to talk about synthesis techniques. There are many different types of synthesis, including subtractive, additive, physical modeling, FM synthesis, granular synthesis. Okay, you get the picture. After lots of research, I finally decided on wavetable synthesis. It's relatively easy to implement and can produce a rich variety of sounds. The wavetable in wavetable synthesis is a single cycle of a periodic waveform. Periodic waveforms repeat, like sine waves or square waves, but they can also be complex, like the sound of a musical instrument or even the human voice. Multiple wavetables can be dynamically modulated and interpolated to produce complex and interesting sounds. In our synth, we'll use 3 wavetables and morph between them by moving the modulation wheel up and down. To generate audible sound, we need to understand the I2S protocol. Here's a signal timing diagram. We can control the clock and the bits per sample, which gives us flexibility when it comes to sound quality. The word select, which selects the left or right channel, is a little weird in that it changes with the least significant bit of the data for the previous channel. Looking at our synthesizer module, we've got this parameter called I2S ticks. This is the number of 50 MHz clock ticks per single tick of the I2S bit clock. We've chosen a sample rate of 44.1 kHz, 16 bits, and 2 channels, which are typical values. Down in the always block, we've got the heart of our sound generation code. Timing here is extremely important if you want to avoid noisy sound. This is where we step through the samples on the wavetables, and here's where we send rendered samples to the DAC. And this is where we update modulation based on the position of the controller wheel. How do we get the sounds into the wavetables to begin with? We load them into ROM, and before we do that, we have to find some sounds and convert them. I found a site with instrument samples where you can choose the pitch and other parameters. We use the free audio editor Audacity to isolate a single cycle. It works best if we can trim the sample where it crosses 0 like this. Now for the tedious part. Our sample frequency is 44.1 kHz, and our note frequency is 440, so we need to select 100 samples. Our synthesizer uses 256 samples per cycle, so we need to multiply the speed of our sample by about 0.392. We'll export as raw 16-bit signed data and open the file in any hex editor. We've got 510 bytes, which means we're one 16-bit sample short. If we did a good job and trimmed near the 0 crossings, the first few samples should be close to 0. We'll insert 2 0 bytes, keeping in mind that this is little endian data, and save our changes. Now we have the raw cycle data, but we're not done yet. Here's the tool I wrote that converts the raw data to MIF format, which is one of the formats Quartus 2 understands. Notice that we swapped the byte order here because I2S happens to use big endian format. In Quartus 2, we fire up the MegaWizard plugin manager, select one port ROM, and choose 256 16-bit words. Then we browse to our MIF file. Finally, our sample is loaded, and after we do this entire process for 2 more samples, we can instantiate our ROMs like so. The only thing left is to mix our wavetable samples together in varying amounts based on the position of the modulation wheel. The math here is pretty funky because we're trying to avoid divisions, and we're also converting to and from 2's complement representation based on the sample value. After we attenuate the individual samples, we mix them at the bottom by simply adding them together. So after all this work, what does it sound like? Well, for my first test, I've loaded 3 different instruments: a bassoon, a trumpet, and a flute, and we can morph between them. Okay, so they're not very realistic because we're not capturing nuances like attack and release times, vibrato, and so on, but it's still pretty neat. Next, I recorded my voice singing vowel sounds. That's really cool. It's like a primitive speech synthesizer. Then I captured samples from another synthesizer using several different resonance and cutoff values. I was trying to simulate a filter sweep, and I think this works pretty well. Alright, let's see what we can do with this. That's all we have for today. Have you ever worked with MIDI or sound in your electronics projects? What did you create? Let us know in the Element 14 community at element14.com/presents. We'll see you next time.
Absolute.